Okay, it's working. Okay, so when I was thinking about this class, and I was thinking, how should I, organize that? And I realized that you guys have a different background. So some of you have not much exposure to molecules. So I'm going to spend a few slides on that, but I'm not going to bog you down with a lot of equation. I'm not going to bog you down with thousands of details. This is not my idea. What I would like to do with this class is to give you a flavor. So what also I have been doing in my research. And the reason why I want to do that is because going through computational work can lead you to different fields. And so I'm going to talk a little bit about most of the topics that I heard today, starting maybe a little bit on SAF on the last day. I'm going to look a little bit at toxicological effect as well. So not only the chemistry of soot on a carbonaceous material, but also other fields where you can expand. My goal is for you to get excited about computational work, maybe molecular stuff. When I am in my ME department, it's always a struggle to find students because historically they come with this background of more continuum or more experimental work. But when you touch about computational and they hear the word chemistry or fuels, they disappear. So it's always hard. But this is not the case. So I think it is an excited field. So I want to start with some expectations. And as you might know, or maybe when you were thinking about this class, this is it's not going to be the history of combustion chemistry. I'm not going to bog us down with the slides about who did this first, what did they do, how the second guy replaced that. That's not my intent. Combustion chemistry is a fascinating field. It's also a saga. It's like something that is worth watching if you want. It's full of brilliant minds. It's full of rivalries also. You go to a conference and sometimes there are people screaming, I did this first, or this is not what I'm going to present here. So let's get just focus on some of the technique. And what I want to do, my commitment to you is to introduce this technique. I'll give you some details. Not too many. If you want, you can definitely, ask me more questions or, if you are to get excited, deepen your interest. But I want to show how you can apply, why this is important. And so hopefully I will only highlight some aha moments in this, journey to nanoparticles and carbonaceous material. So I was thinking of this is not what we are going to do. So we are not going again. I was having like just a Netflix soap opera about people who did that, and now other people complain. So no, you will see references, and at the end of the slide, usually I will provide also the reference that I have used. So what is going to be this journey together? The first thing, the theme of this class, I was thinking a little bit, and so I thought, what about the molecule and dancing a little bit? That's usually what I look at when I do some simulations, and just I want to, if may transmit this kind of feeling that I have when doing the simulations. And so I want to start with a couple of points more for introduction. So what I call the invisible dancer, and that is carbonaceous material and soot. Has been with us, with humans, since forever, basically. Not only that, but the history of soot is really intertwined with humans. And in many cases, I'll show you, that's what soot defined what happened to humanities. If you think about progress or industrial evolution, soot was a big player. So invisible dancer for me is a soot and what the role has had in our civilization. We will then move to some quantum chemistry. And so again, I'll give you some background for a little bit and then move into the application. So why we use quantum chemistry, and I call the quantum ballet of bonds, I know, but it's basically about understanding how those molecules, the reaction and the pathways can happen, and we'll focus on the gas phase. Then I'll move to a different choreography that comes from Monte Carlo techniques. kinetic Monte Carlo. And this is one of the things I'm more excited about. So it will be tomorrow, but I will tell you more about some of the things that we've done in this area and what kind of advantage do they have, why we did that. So what you are going to see through this journey, that is a little bit also my evolution over time, is that, I'm always interested in why. Okay, so why I see this the experimental evidence, what can I do then with my technique to study that? One of the last points then will be molecular dynamics. So why we want to use it, what kind of information, additional information can provide compared with the Monte Carlo and quantum chemistry. And then the last one that, where did he go, the guy? So a little bit of AI. Okay, we've done some work on the AI applied to molecules, and I want to tell you why it's needed and what kind of data you can get out of this. They are very much intertwined with the molecular simulations. So when you do molecular simulations, you have millions of trajectories that you need to analyze. Okay, I'll show you that. So how do you get an output? Because when you talk with other people, maybe company, but also people do Soot modeling like from an empirical point of view, they don't care about all my molecules. They care about a number. They want to know, okay, tell me the rate. Okay, that's the question I have. And so my goal is to get from molecular here all the way to a rate, for example, or a parameter that can be fed into some more empirical models. Okay, so sorry about this, but just to add to my story yesterday, my PowerPoint is not working on this computer. So whatever mistakes or things I left undone before coming to Princeton, they're still there. So bear with me, some slides are off. So invisible denser. Why this is interesting? So I want to briefly mention that we have records of, they go over 35,000 years for carbonaceous material. 35,000 years is a huge order. And this is an example. This is the Chauvet cave in France. And what you see is this charcoal that was used from pine to draw. Okay? So if you just think about this, humans to do that, they had to produce this charcoal. They had to burn some pine also. And they used to paint those caves. Sorry. Then we move, this is historically, to this TM of soot particles. That is more what we have seen in the last years or so, decades or so, this new technique. And now soot, before it was a decoration, a painting, now becomes some kind of image like this. And lastly, I will say, if I had to point to 3 different areas, is the last one, in which we talk about carbon, nanoparticles, more general form, and health effect as well. Together with, for example, cancer is one of those. Oh, thank you. And then environmental effect. So I want to just, again, glimpse over those concepts with you. And if you, thank you. Okay, so 1 second, this is another thing here. And you see all my problems? Oh, no. Okay, shift. So he added the device to the computer, and now the computer is the keyboard. I cannot identify. Okay, so shift, what do you want? Okay. Oh, continue. I have no idea what's happening. That's fine. I can wait. I think this is enough. I can just use this. Yeah, so I don't know what, ignore it. Yeah. Wow, that's the best thing. You always either reboot or ignore. That's what I do. Okay. Okay, so it's working. Now let's go. Okay, more details about this because I find them fascinating, so you bear with me. This is 33,000 years ago, okay? And again, this is France, Chauvet, and this is Lascaux, same in France. What's interesting is that the use of this black again, the black paint that was carbonaceous materials. And just if you're interested, 33,000 years ago, they used to paint lions, panthers, bears, so aggressive predators. 23,000 years ago, it was more like a bull, man, bird, so something like not so aggressive. But the main point here is that this is what it was doing. So they were burning somehow, in this case was pine, for example, producing soot again, or carbonaceous material of some form, and then used to paint those ones. We keep going briefly with these things, but you know, how many of you knew the 8C? The 8C, so many of you might know that, but it was based on forensic analysis of, they found the tattoos on the body. There were 3,300 before Christ, basically. And so again, why am I showing you this? Because those tattoos were made based on soot, or carbonaceous material. Somehow humans had found a way to collect this as soot and also use it, whether it's painting or maybe this was also for injuries, of course. So humans and soot intertwine for many reasons and for a long time. So this is something else, a Chinese, no, doesn't go right. Oh, it's working, good, great. Okay, inks, that was for calligraphy, that was actually a recent paper in 2022. So this is a very old effect, or a very old, you know, something that people did, but there is still a lot of study going on, 2022 Nature, to understand what is the ink, what is the brown material, the black material, the soot. And then we move also to the Romans, so this is Pompeii, in Italy, but they produce burning the dregs of wine, with the best wines producing a blue-black color similar to indigo. Okay, so this was a lamp that they basically structured for those kind of emission. So fast forward 30,000 years ago, cave art, Etsy is one instead with tattoos on injuries, that was that, and then illumination for this Pompeii. Okay. So if I had to briefly summarize those, the 3 ages of soot, and I will say the first part is a kind of illumination. So soot by design, but mainly for light. So think about that. So prehistory until I would say 1850. And so the cave painting until maybe Faraday's candle. So the experiments that I'm going to talk in a moment about this. The second part, industry. Soot as an industrial gold was a period. Steam engine, something that you might have heard, until there was also a big London smog that killed 12,000 people. And then the third one is more about inhalation. So soot as an enemy from 1950 to present. And I want to show you a couple examples of this. So again, dancer that is not, maybe is invisible dancer, but has been with us for different application or used in different ways for many, many years. So the first one, as I was mentioning, is this a cave painting, right? And so that kind of timeline, if I will say, it will stop in 1850, it is 60, when Faraday gave these lectures. And, you know, it's famous, so you might already know that. But I will say this is a moment in which combustion became science. And so you can enter, what he said, there is no better, there is no more open door by which you can enter into the study of natural philosophy than by considering the physical phenomena of a candle, okay? Very complicated. So, and he shows a lot of principles that are starting to be related to the chemistry of things. And I try to find something, one of the interesting ones. And so one of the part of this experiment of this lecture that was interesting, let's see if it works here, something that looks like this. So what he did, and I tried to, is that if you blow out the candle, basically, it can reignite. Okay, so what basically was done is that the candle was off, and then there were fumes from the wax that was burning. And what he showed is that you can reignite the candle without touching the wick, right? So this was one of the many insights from that lecture, but it starts showing that what he was burning is basically not the solid wax, you liquefy, and then not even the liquid wax, but then it becomes gas. And more about this combustion science aspect. And this is one of the aspects in which, again, you reignite, because in the smoke you can find unburned wax still for a while. So what happened the second part? So the industry. And so let's see what happened. The reason why I have this one is because, as you can see, and again, when I said that it shaped also humanity, is that we went through this industrial scale-up. And so carbon black production becomes a big deal. A big deal when there were tires as part of the tires development also. With printing was another big deal also. And so here I'm just showing you a couple of examples. But whether it's inks, is carbon black in tires, is coating, you saw a huge increase in the carbon black production. 1920, I had 100K tons per year. In 1950, 1 million tons, and today is 15 million tons. So huge increase in the production of this material. The last one is the inhalation. And so people start realizing, especially with the London smoke event here, that so what happened here is that 12,000 people died for this event, basically 12,000. And people start looking in a week. So first of all, I should say in a week, 5 days or a week. And so what they found is that this black material inside those bodies. Okay, so they start having some evidence that actually you are inhaling this black material somehow. When I talk about black material, maybe I should be more precise, carbonaceous material, because I'll show you that it's not only soot, it's also what comes before that is dangerous to the things. And so many of those things are, dangerous. And then one of the latest one, the London smog also is important because he prompted the Clean Air Act in 1956. So that is a big deal for the emissions of soot. And so that's the reason why I put here as an ending point. And then the last one is what's happening later today. And I'm sure that when you talk about health effect or exposure, you heard this a few times, like you heard the climate change. So I'm going to give you a different spin, and I want to talk about the ice melting. That is it's very interesting to me. So first of all, how we are exposed, ingestion is one. You know, when you burn, you make your meat on the barbecue, that black things, that's some kind of soot that, in principle, you don't want to eat. Dermal contact, but also inhalation. Those are some of the routes. And this is an old event, but in which basically they noticed cancer in, this is the doctor that did a study in the 1700s, and the chimney sweeper's cancer of the scrotum that they found. Okay, so they start having some evidence that exposure could lead to some health effect and cancer. Okay, so health effect, environmental effect, and I'm sure again you heard a lot about environmental effect, climate change. So I want to give you a different one here. What happened is that because of the consequences, one thing that I'm more interested in is the permafrost thawing. So you might have heard of that, but what happened is that when you see the melt of those glaciers, you have an exposure of humans and animals that died from infectious disease, right? They release pathogens that were previously locked away. So what happened is that those melting glaciers release microbes into the water stream and the rivers. And so in 2016, there was a Siberian anthrax outbreak. There was a thawed reindeer carcass from melting permafrost that basically managed to spread all those microorganisms that cause infections. Just curiosity, what they call is a giant viruses. So researchers have found also what they call zombies viruses. They are 48,500 years old in these things. So this to me is very interesting, and I want to show you, hopefully Wednesday, if I have time, that I have done some work with microbes and bacteria. And one of the things that I'm very much interested was looking at the interaction of carbonaceous material with microbes. Okay, and so from this bigger picture, I'm going to show you how you can, with the computational method, look at the interaction, for example, of carbonaceous material, whether it's a quantum dots or a small carbonaceous material, with some of those microbes and what kind of effect then they have. So I'm giving this introduction slide because it's a little bit what I have done. So starting from, we can talk about the fuels, we can talk about the carbonaceous material, but I want to jump also a little bit of the kind of biological application also, if you want. So we talk about soot, but if I say soot as a carbonaceous material, then I am broadening this topic way more. So another way to look at soot is nanomaterials. So actually the dawn of nanotechnology, okay? So as people started to sample more combustion systems and they had ways to identify the materials, well, one of the important things was the transmission electron microscopy, TM, because it confirmed that carbon black wasn't just amorphous, but was comprised of a lot of nanoparticles. Okay, so as the techniques evolved, the insight, we gain more insight, and so carbon particles means a lot of things. And those carbon nanoparticles then coagulate or assemble together, and they grow into this soot that we are we've been talking about. And so this is important to understand, as I was mentioning, the property and the industrial application, they changes also with this. More with nanotechnology and more push for carbon materials from the flames. Feynman, he was not talking about soot, but was to see there is plenty of room at the bottom, not specifically about soot, but it starts conceptualize nanotechnology, so the manipulation of atomic level. So what happens now for nanotechnology is that people design materials, right, that you can synthesize in flames. So this is a completely new venue that has opened to this field. Combustion research also began to, the research started to unravel the chemical pathways for pHs. TM remain an important tool for this. And they start having some ideas about the morphology and the structure of soot and materials. So these are some of the suggestion and the visualization that they had at the time, how soot could be formed. Those are layers or graphene layers, for example. So there is some aromatic content, and this is the structures, some of those. And more of this, you can produce all this in flames, right? So discovery of the fullerenes in C60 in 1985. This was very interesting, of course. It was the confirmation of the spherical cage-like structures of fullerene once they were isolated again with the TM. Then nanotubes, everything that you heard, I'm sure. So high-resolution TM also provide confirmation of these hollow structures. So without EM, and that's the reason why I mentioned before, those breakthroughs will not have occurred. So it really helped to push these boundaries here. So carbon nanoparticle is what we are going to focus on, with a broad meaning that go from small structures. We'll talk about pHs. We're going to talk a lot about nanoparticles, okay, that are really the precursors of this soot that you're looking at. So carbon nanoparticles today. So I'm from the cave. I'm bringing you to right now. You talk about soot. Soot is definitely very interesting, the modeling of soot carbonaceous material for many applications, as you heard many of you doing in the research. But it's also an exciting aspect to design nanomaterials. So one of the applications right now is the carbon material for cancer, for example. And so what they do is they create some specific shape of nanoparticle, they attach some receptors, some modification, and so this is one of the latest applications I found, is specifically, so you have different nanomaterials here, and apply for cancer treatment as well. This is instead the nanotubes. They have some property of the material, like strength is one of those. And so I've been applied in many, many biological application or medical application here, orthopedic application, for example. This is a knee, this is a, one of the bones here, replacement for things, and also for dental application in those things. So there is a lot of bad, there is a lot of new stuff and exciting stuff if any of you is interested in this topic. Okay, so let's take a look at more details about this candle. So I want to show you what do we see when we see a candle like this. So this is just some basic representation of the candle flame, and this was taken from this anatomy of Christmas candles. So there's the reference here. But basically, what you see here is different temperature in the regions, depending on what you are burning, what products do you have. And so there is the luminous soot, that of course is the yellow part. There is a part here that is more the oxidation, where the oxygen can react with the fuels. Then there is this blue-green luminous zone and the dark zone. So candles, you have the wax that vaporize, you might know that, of course, and once you ignite, that's what you see. So let's try to understand a little bit better what's happening here. So visually, if you do just a simple experiment and you put a metal in this candle, so what you will have is, let's see, so this is three different things. So if you put the metal on top of the candle, you get water vapor, right? If you put a spoon in the yellow luminous part, you get the black material, soot. But if you put it very close to the wick, then you get the white wax. So simple experiment, this is a metal, but it shows that the products that you have are different, of course. And so the yellow relates to the soot, but here there is a lot of the chemistry going on between still the molecules of the wax and what we'll see in a moment as oxygen as well. Another, so let's show this, okay. Another interesting thing that I wanted to show you is that candles are hollow. I don't know if all of you knew that, but so this is just a candle, and from the top they are adding a metal wire to the thing. And so if you get closer, and I don't know if the videos can see very well, but it's a hollow, okay, in the middle. I thought this is very cool also. So candles are in some ways very beautiful for many reasons, and I'm sure you have studied them in details. So what I'm going to do here is basically give you some main regions of the flames. I had another movie, let's see what I had here. Oh, this is basically showing the buoyancy that you have for cold air and warm air and how you get this shape of the candles, okay? Some basic information, okay. Now, one more, okay, this was supposed to come before the candle, so you bear with me here. I wanted to add two more materials that are very interesting. So graphene, 2004 was also isolated in flames with all this technique, AFM, TM. And more today, as we heard also, people look at the combustion from a more advanced technique. So there is a CFD, molecular dynamics, laser diagnostic also is, and as they evolve the tools, we gain more insight. So what do we do here? We are going to do something like that. That is basically, this is your candle, and I show you some of the features of this candle. And I'm going to shrink down and try to understand what's happening instead to my molecules here, okay? So no macroscopic processes, but more narrow down on this. And so this was initially developed by Bochern in 1994. It was a picture that he put together. But I'll show you also how I changed that a little bit. So let's go step by step. At the beginning, you have some fuel. It could be the wax, of course, that you have here, reacting with the pyrolysis, oxygen, or reacting with oxygen. And you start either to break down the fuel a little bit, so you have those small fragments, that then they start to recombine into bigger structures. Okay, and those are called pHs formation. Okay, some of those are carcinogenic. Many of those are carcinogenic. So one thing that the community is very much interested in is that can we develop mechanisms to predict from the fuel what kind of species we form and how much of those, okay? So this is interesting. This is all a PhD student could do that. So just this question will take, maybe multiple PhD students. So there are a lot of mechanisms available in the literature right now, but still, I will say that the agreement between modeling experiment is still not great, okay? So there is definitely some condition that works well, others don't. So one theme that I'm going to show you in this presentation 3 days is that I'm always very interested in developing something that is general. I don't want a mechanism or an idea that works only for that flame. Okay, so, and this is what I have seen a lot also in the literature. So I have this great model that works here, but then now I move with, I don't know, ethanol and ethylene, and it's not working anymore. So this is the first thing, pHs. I also, there is the lecture by Professor Kern that is going to talk all about this stage here. The chemistry, the basic chemistry, what are the reactions that that takes you from the fuel all the way here, okay? So if you're interested. Once you get to this pH formation, what's happening now is a big jump, is a leap, because honestly, there isn't a lot of information here, even experimentally. And the reason why there is no much information is because the time scale is very short, the temperature is very high, and it's a very reactive environment, meaning that the reaction happens so fast that, the technique that can identify those are limited somehow. And then once you form those inception, nucleation, these are small nanoparticles between 2 and 10 nanometers, they start to agglomerate. You can see they get together, they get bigger. And then there is addition also the pHs on the surface of this. And then as you keep growing, you get agglomeration, oxidation, until you get those fractal clusters that you might know as soot. So I'm going to focus mainly on the most challenging phase, I think, that is this one. These are precursors to soot. If you have a way to predict this process of this transition well, you have a way to predict soot also, okay? So we will go, I will show you some quantum chemistry, and the quantum chemistry is mainly used in this area. So can I find some molecules or pathways that go from a fuel all the way to the formation of pHs? The second part is going to be a Monte Carlo story. And the reason why I'm a Monte Carlo is that now you have all those pHs in your pool of molecules. What happened? They can do so many different things. How can you study this? Okay, can you go from those small, let's say this is a pyrene, that is a very famous compound in combustion, all the way to molecules that have millions of carbons? Okay, how would you do that? There is no way you can do this with a mechanism like the one that you will use from fuel to here. Okay, I have millions of reactions happening and way more of intermediate species. Now, you say, I don't care, or maybe this is not relevant. The reason why I'm doing this is so, molecular level, because what I was interested in was, as I told you, also the health effect. Without a composition, without a morphology, you cannot predict. And so the goal was, can I go from maybe some pHs all the way, can I jump here, but still retain morphology and chemical composition? So not an empirical model in which, I have AI plus AB, whatever, and they becomes, or spheres that become something else. I wanted my chemistry of those things. That was my interest in the story. I also was mentioned that this is one of papers that was published in 2019, and this is the group in Italy as well. And this was very interesting. There's been a lot of experimental work, and I'll have all my reference in the slides. But the reason why I want to highlight this is because, so for the first time, what they did, AF image of molecules found in soot particles. Why this is interesting? Because those molecules, the current soot modeling cannot predict those. So if you apply the soot modeling that you have right now, you go to the literature, you download whatever you like it, and you say, okay, start reproducing those structures, you will have troubles. what you see in the structures, they look like a pH, so they are looking like this, but they have oxygen, some of those. They have aliphatic chains, they have 5-member rings. So there is a variety of structures here that, for example, it's a 5-member rings, that current methods could not do. And so that's the reason why, those are another supporting reason why I was very much interested in not losing the chemistry. I want to move up in scale, retaining my chemistry, okay? So we will talk about this, and I'll show you how we can model this one. So, another important part is that, we go back to this one, to the slide I just showed you, but who told you this? So right now, I told you TM or EM techniques can help you look at a soot as some of the materials, but who told you that when you jump, you go through those nanoparticles, okay? And so another important experimental story here that I want to mention is that some laser technique. So the materials, when you look at this transition, there are two major classes of carbonaceous material that you can look. So there are nanoparticles with size between 1 and 5 nanometers range, and then soot particles, as you grow and you go to the primary and then bigger soot, 10 to 100 of nanometers, okay? This nanoparticle, that's what we are going to focus on, they have unique chemical composition and morphology. They are emitted. This is the one we breathe. There are also the ones that you cannot stop. So when you breathe soot somehow, you can stop them in the nose, in the throat. There are mechanisms for that, but those are too small. So paying attention to those is very important as you want to maybe assess the health effect, okay? Same scale material is the one I've been using for bacteria that I want to show you on Wednesday. So to me, those are the challenging ones, but also the more exciting in this story for carbonaceous materials. So they maintain molecular characteristics, and they have some transport and surface phenomena typical of particles. So they are really an hybrid in this thing. So, where did this come from? So there was a lot of experiment. Well, this is a kind of more comprehensive articles, 2009, sorry. But there has been a lot of work done on this laser technique. And then what's important was the first in situ evidence of nanoparticle in premixed freight from mass spectrometry. There was from Hohmann and Wagner in the early 60s, if you are interested in that. And then Grother in 2004 also did something similar. And what the comment was that these high mass species with the masses range from 600 to 2500 were pHs containing 5-member rings held together by the van der Waals force, and occasionally by a carbon-carbon bond or chain. Okay, so this is something. The group in Italy also, the lesson 92, 94, developed this absorption technique to identify species that were transparent, so they don't absorb in the visible to visible radiation, but absorb in the ultraviolet. So this tells you a lot about morphology. Is important because I cannot just say that they have the same composition, so nanoparticle and soot, because if you look at the optical behavior, soot absorb in the visible, nanoparticles do not. And the reason why it's not is because they have different chemical composition and morphology. So again, if you want to be predictive, if you want to reproduce what you see experimentally, then you need to be detailed and you need to be preserving some of the chemistry and morphology if you want. So this plot just show you, this is the distance from the height from the burner. So you have a premixed flame with the burner, and then as you go, 0 is the burner, and then you go up in height. And this is the scattering that was measured. And the main point is that at 266, so in the ultraviolet, for an ethylene air flame, so those dark triangles here that you see they go up, they are the scattering in excess to gaseous species. So whatever is making this line go up is more the gas phase species. So you're transitioning into those nanoparticles, okay? And so that was the first, one of the first insights for this, done in flame. one of the issues that sometimes when you take it out of the flame, things might change. So this also is one of the reasons why this is an important study. And so the optical data show the presence of those two classes. And here I'm showing the height above the burner. This is the diameter. This is the concentration, number concentration. If I ask you what's the concentration of those nanoparticles, you should know that, okay? Because it's a number that is high, it's important compared with soot. So what you see is the volume fraction. So what I'm showing you is a distance from the burner. So let's look at number concentration first. This one is the nanoparticles. This one is soot. So if you look at the diameter, this is the small diameter that you have here. So they have a higher number concentration, right? And a very small diameter. And then as you start with the soot formation, there is also this number concentration that decline. Okay, so first range nanoparticles, higher concentration that you see here, and then eventually you turn into soot. But there was an excess of scattering, saying there is way more the gas phase right now, okay, for those systems. So now, again, the reason why we are interested in those particles, and again, it's because small has a lot of advantages. So you can have material, but it's also bad for the health and the environment, the way we interact with that. And so I want to show you some of key studies through the history. So the first one, this is over Dorster, this is 2002. And it shows basically that those nanoparticles, the one I just showed you, the less than 5 nanometers, actually are the one that can translocate. So they deposit in the lung, you breathe them, and then they're able to translocate to other organs that are outside. So one of the things I have done in my study, and I'll show you again maybe if I can, is that if I have a nanoparticle, can I show how across the cell membrane? So he's telling basically, they goes in the lung and then they cross cells to get to other organs. So my question for this case was how fast and how much the shape and the chemistry of those nanoparticles influence the process, okay? And so they discussed findings from animal studies showing particles in liver, heart, and brain. So they move, they translocate. And so the paper helped to establish ultrafine particles, so there was a distinction here. And then this is 2025, this is the latest paper from the same group. They're still looking at this, but now they have additional information here in which they claim that the exposure to those nanoparticles disrupt brain regions, so they disrupt coordination, and they contribute to neurological disease like Alzheimer also disorders. So we're going way higher in this. So what I'm showing you, and this is rats, an example out of the male rats, and all those to tell you that those are all connections that the brain does somehow, and you see that especially in those regions, once they are exposed to high concentration ultrafine particles, those of the connection are going to change. So the probability that they connect, for example, from something that is blue here, you see here the blue that is 1%, so I make a connection with the brain, then here it becomes red. So what is basically showing is that the presence of this material influences the connection that the brain is doing for different activity, including neurological disease. Okay. So this was another examples, but again, my point is that those ultrafine are the one we should look at, and the one we should worry about for many reasons. And so this was in humans. The one before was in rats. That research group doesn't do humans, it only does rats. But here, this instead was humans. And so what they saw is that they, of course, radio-labeled nanoparticles that were inhaled by those volunteers. And is a human evidence, just an animal, as I said before, that nanoparticle can enter systemic circulation. So they went this, and then they found the nanoparticle all over the body here. Okay, so this is the bladder that you see, but it's also, this is the liver, this is the bladder. So eventually, they get in the bladder also. The bottom message actually is that no matter how long you wait, the body will retain some of those nanoparticles, so you will always find them inside. It's not able to excrete those. So one more things about, sorry here, carbonaceous nanoparticles, some of the respiratory disease also, besides asthma. So this is a lung disease, so they have lung cancer, lung disease, lung fibrosis, lung injury, in which they saw they were interested in looking at the interaction of nanoparticles with the biological system as well, and how they affect all those processes. Again, this is a new, relatively new paper, so people still don't know a lot for these things. Last one, cardiovascular disease. This is a very depressing point, but again, I want to give you option. Maybe you like to do health or toxicology in the future, and some of the things that you can link is what you're learning about soot, how they look like, what the shape and the chemistry, and how they can interact with those. So respiratory disease, cardiovascular disease, inflammation, neurological effect. Some of the examples are here with some of the reference. And again, this is all new. So people are wondering, people are worrying about all those things, and it's not a done deal. It's not that people are completely aware. This is more a summarizing slides, but another thing, of course, is wildfires. That is a big deal. And cardiovascular health. This is, again, 2024, and they show the mechanism that basically are affected by the exposure to wildfire emissions. So how you inhale those. Again, what are the different processes, respiratory, nervous system, cardiovascular, but how the different particles can affect some of the mechanism here. Again, translocation. So translocation is a keyword. They move. You get in the lung, you find them somewhere else in the body, okay? And that is due to chemistry. If you know the chemistry of those nanoparticles, you can predict somehow if they will move or not. Or if you want to be proactive, let's say that you are designing a nanoparticle for cancer, knowing that that chemistry translocate faster or slower help you. Okay? So, or developing drug. This is the same thing. So you can see those tools as passive, in which you try to understand a phenomenon, but you can also be active and say, okay, I have this tool. Can I use it for something else also? So let me give you some key takeaways from this initial introduction. So the soot has evolved from ancient art to industrial uses. That's what I think. Flames are a very complicated system. There is a lot of literature, history going on, and there is experimental tools and modeling has been intertwined forever, advancing each other along the way. Particles in flame, carbonaceous particle in flames, 1 to 5 nanometers nanoparticle, they are responsible for this inception. They are really what define the transition from this gas phase to soot. And so that step is critical. They are UV transparent, and instead the larger nanoparticle, soot particle, they are more absorbing in the visible. So that's the black material. And these particles have a deep effect on body, respiratory, cardiovascular, and even on DNA for the system. So thank you for bearing with me for this brief introduction. So what I'm going to do now is that I want to lead you to the next topic. And so what is the challenging? Can we understand how they get together? Can we understand how those pHs are formed and how they transition to nanoparticles? What is driving that? And so what are the chemical reactions also driving their formation and their pathway? And so what we need to do now is to jump into a little bit of the quantum chemistry, and then I will tell you how it's been applied to the combustion, what kind of results you can get from that. So one last slide before we take a break, this one. You saw the initial graph that I showed you. So again, fuel, gas phase species, then nanoparticles, then they start to agglomerate and then eventually transition this visible soot. I am interested, very much interested in the thing that I have developed over the years are for these transitions. So I didn't want to jump from a pyrene to a spherical particles. I just wanted to follow the growth of these materials. And so instead of having like a spherical particle, I kind of, if you want to blow up this section, in which you start building those nanostructures and really see how they evolve. This is an example of this. Some of the pHs grow in some conditions. And so you see some of the weird structures and rings that you have here, aliphatic chains. But again, my intent is to reach, for example, 2-3 nanometers without losing track of how the chemical composition and the morphology of the structures. Okay, so I think we can take a quick break here and then we'll jump into the quantum chemistry. Any questions for me? It's been a little bit of introduction, but again, the intent is that this is cool in many fields. Okay, so not only combustion, and soot, but you can do a lot. Yes. Yeah.
For those fractal clusters that form after oxidation,
yeah.
Are there when we typically measure those, for example, in a condensation particle counter, we get the mobility diameter.
Yes.
Or the minimum mobility diameter. So would you say that the that those clusters that have those fractal shape somehow travel as fractal form and their mean diameter or aerodynamic
yes.
diameter is,
yes.
is the
yeah.
mobility of a sphere?
You want to say something? I should? Okay, yes, yes. So what happens is that initially you have those oh, okay. Sorry for the camera. So the question is that, so those are some fractal clusters that you have here over there, and then there is also a diameter that you read, correct? And so definitely they are related to those structures that you see up there, okay? So the idea is that you have those first, what I call macromolecules, nanoparticles, that actually looks like that. They will start to assemble, and then you have those initial steps that you see here. Those primary particles, you have some of the gas phase attaching, and then eventually you form those fractal structures that you see here with the diameter that you read. Yeah. Any other question? Okay, then I'll see you in 10, 15 minutes.